We're now going to look at inverse functions. And before you look at this, you may want to go back and review the definition of our function that we talked about, and we looked at those four different characteristics. A couple of the characteristics we talked about was that your x value must be paired up with a y value in the range, and we cannot have repeated x values. So if we look at an example here, if we have our domain, which again, that's our x value. So we're looking at the domain of our function f, and I'm just going to say our domain is very simple, 0, 1, and 2. So these are all the x values that make up our domain. And then I'm going to say the range of function f is very simple, and I'm just going to call that 2, 3, and 4. And that would be our y values that we would get out. So what we're saying here is we have some function f of x that takes us from the domain here over to the range. And that function could be very simple as x plus 2. And you can see that if I was to plug 0 in for x, we would get 2. If I plug 1 in for x, we get 3. Plug 2 in, we get out a 4. So this is just our basic function. Every x is matched up with a y. We do not have repeated x values. So now we want to look at how do we find the inverse of this function, or what is the inverse? Well, before we get into the inverse here, I want to show you the notation for our inverse function, and that is simply f to the negative 1. Now, this is written like a negative 1 exponent, but that has nothing to do with a negative 1 power or exponent. The negative 1 is just simply the notation we use to indicate that this is the inverse of function f. So here we have our function f of x is x plus 2, and we want to find this inverse of the function. So what that means is we want to find the function that will now take our y values. If we plug them in, it will take us back to the original domain. So over here now, what we're going to say is this over here is going to be the domain of the inverse function. So the 2, the 3, and the 4 are going to be our x values, if you will, for the inverse function. And over here, we're going to have the range of the inverse function of f. So over here, the 0, the 1, and 2 would simply be the y values, or the range of the inverse function. And the inverse function here of our function f would simply be x minus 2. And I think that's kind of obvious in this particular example, and we'll look at later how we can find this inverse function. But if our function is x plus 2, it would make sense that if we want to go back, we would have to kind of do the opposite and subtract 2. So let's kind of look at this example using a table of functions here. If we have our function, let's say x and f of x. So here's our x and y value for our original function x plus 2. So if we plug in 0, 1, and 2, we get 0, 1, 2. That's our x values. And we would get out our y values over here for f of x, which would be 2, 3, and 4. And then if we were to look at the x values and the y values for the inverse function, well, the x values then for the inverse function would be the 2, the 3, and the 4. And we want to get out the y values over here, which would be 0, 1, and 2. So if you look at this carefully, what have we done to the domain and the range? Well, over here, this is our domain, 0, 1, and 2, but over here, the 0, 1, and 2 is the range. And over here, where we have our range of our function f, that is the domain of the inverse function. So if you notice here, what have we done with the domain and the range? We have simply switched places. The domain for our function f is the range for the inverse function, and the range of our function is the domain of the inverse function. So essentially what we've done here is we've simply switched our x and y values around. So if you were to look here where we have 0, 2, over here we have 2, 0. So in other words, where we have the point 0, 2, the inverse function would have 2, 0. So again here we're switching around our x and y values. So where here we have 1 and 3, we now have 3 and 1. 2 and 4 for the inverse function becomes 4 and 2. So the function f of x takes you from these x values to the y values over here on the right. The inverse function takes you from the 2, 3, and 4 back to the 0, 1, and 2. I always like to describe this if you've ever used Google Maps to find directions. If you want to use your directions, for example, to go from point A to point B, you get your directions from Google Maps. And then how do we get back from point B to point A? That's where you would hit the reverse route, and that gives you the directions to take you back. So you could think of this as your function to take you from A to B, from one location to the next, but then if you want to get back home, maybe you still need directions, and the inverse function is what brings you back. So you can kind of think of that using Google Maps, using that reverse route would kind of be like your inverse function. It kind of brings you back to where you started from. All right, let's look at a property here of your inverse function. Functions f and g are going to be inverses of each other if, and you'll see this notation here when I write this, this is read if and only if. Okay, so that's what this IFF means. I didn't misspell it. This stands for if and only if f of g of x, so there's our composite function, f of g of x equals x, and g of f of x also equals x. So if you know that f of g of x equals x and g of f of x equals x, then we will have inverse functions. Now let me quickly explain here, what does this if and only if mean? If you're familiar with an if-then statement, if A happens, then B, well, normally you can't really necessarily always read that backwards. If A, then B does not always mean if B, then A. Well, what this if and only if stands for, that says we can read this statement forwards and backwards. For an example, if functions f and g are inverses of each other, then f of g of x equals x, and g of f of x must equal x. Now, what the if and only if means is we could read this statement backwards. We could start at the bottom and say, if f of g of x equals x and g of f of x equals x, then we can conclude functions f and g are inverses of each other. So that's all that the if and only if means. That means you can, if you know one is true, the other is true. So if f and g are inverses, then the composite functions here, f of g of x and g of f of x, both will be equal to x. And also the other is true. If we know f of g of x equals x and g of f of x equals x, then the two functions must be inverses of each other. So let's look at an example of what we mean by that. If we have, say, for example, our function f of x equals x cubed, and you probably can guess, and I'm going to go ahead and tell you here, the inverse function is simply going to be the cube root of x. Now, let's verify that. So if we want to use the statement above, then that means f of g of x, well, our g of x here happens to be the inverse function. So if f of f inverse of x, we want to show that this is going to be equal to x. Well, certainly if we take the inverse function, which is the cube root of x, and we substitute this in over here to this function, then in place of x, we would have the cube root of x, and that would have to be cubed. Well, hopefully it's clear then the cube root and the cube would cancel, and this would certainly be equal to x. Now, that doesn't prove that they're inverses. We have to look at it the other way. So, for example, then f inverse of f of x, what does this equal? Well, that means we're going to take function f, which is the x cubed, and we're going to substitute that in over here for x. So that means we would have the cube root of x, well, our x cubed, so it's the cube root of x cubed. And again, the cube and the cube root is going to cancel out, and we're simply going to be left with x. Now, because that these two are the same, equaling to x, now they have to be equal to x, not one is x and one is negative x, or if they both equal 5, they have to both be equal to x. So therefore, that tells us that these functions are inverses of each other. So that's how we can test for functions to see if they're inverses algebraically. And if we want to look and determine if functions are inverses graphically, let's look and see what happens if we graph each of these functions. Well, if we were to graph x cubed, we know the cube root function looks something like this. So here's our function f. And then if we were to graph the inverse of f, then it's going to look something like this. Well, if you notice what's happening, well, if I was to draw, if you recall the name of this function that goes right through here, this is the identity function y equals x. If you have two functions that are inverses, then they're always going to be a mirror image. In other words, they're going to be a reflection or symmetric here with the line y equals x. So if I was to fold the paper here on this line y equals x, function f is going to fall on the inverse of f, and the inverse function would then fall on top of the function. So they're always going to be symmetric here with this line y equals x. So that's how you can determine whether functions are inverses or not, by looking at the graph. All right, so inverse function simply takes your function back. So if your function is x plus 2, the inverse function is x minus 2. So that means if you plug 0, 1, and 2, you get 2, 3, and 4 out. That gives you the range. And then if you want to find the inverse function is going to take you back to the domain. So again, essentially what we're doing, if you look at the ordered pairs, you're switching the domain and range, which means you're switching your x and y values from the function to your inverse function. And that is why they're always going to have this symmetry here, this reflection about the line y equals x, because you're switching the x and y value for your function and your inverse function.